Hey everyone, Tom here, and back when I made the solid state relay video, I got lots of questions on, well, can I use them for 12 volt DC heated beds too? And while there are DC in, DC out solid state relays, in most cases a simple MOSFET is cheaper, smaller, and will perform better. So in this video you're going to learn about what makes a good MOSFET for the typical 3D printing applications like switching a hot end or bed heater, and how to wire it up. So there's one big difference between how you can use an SSR and a MOSFET, and that's isolation. With an SSR there can be an electrical potential of a few thousand volts between the switching and the switched voltage. That's why you can easily use an SSR to switch mains voltage with an Arduino without having to worry about stuff melting down. On the other hand, the way MOSFETs are typically used for switching simple loads requires your control signal and your load to share the same ground potential. So if you have two different supplies for them, like a 5 volt supply for an Arduino and a 12 volt supply for a load, you'll need to have the ground lines of those two supplies connected together. If you can't do that without damaging something, you'll need an SSR, but typically you want to have all ground lines connected to protective earth anyways, which means a simple MOSFET will work just fine as well. So there are two main parameters you'll need to know when choosing a MOSFET. One is the voltage your load runs at, and the other is the sustained current you want to switch. To gauge if a specific type of MOSFET will be able to handle those, you'll need its datasheet. In my case, as an example of a common IRLZ44N. And yes, a datasheet is big and scary and has lots of information you'll never need, so I'll try to break it down as simply as possible. So I'm not going to go for 100% perfect technical accuracy, but for good enough for 99% of all applications, even if we're going to take a shortcut here and there. Now, the shortcut I see a lot of folks taking way too often is simply jumping in and seeing the 55 volt rating and the 47 amp rating right below that and going, well, 47 amps is way more than I'll ever need, so it's probably going to be fine, right? Wrong, because it's not that simple. All that 47 amp rating says is that the MOSFET will not melt down internally at that current if you can provide infinite cooling, and you probably can't do that. So if you actually push 47 amps through this type, it's going to generate more heat that it can dissipate, overheat, and melt down within a few seconds due to the internal losses within the package. And most of the time that's going to be your limiting factor. So how do you figure out how much a MOSFET can actually take? Use the third value up there, which is the internal resistance of the FET when it's fully switched on. That's going to determine how much power you're going to need to dissipate from the MOSFET's package at a given constant load. And constant for most electronics without huge heat sinks is longer than about 10 seconds, which you're easily going to see in any heater application. So the RDS on for this particular type is 0.022 ohms, 22 milliohm. In a perfect world. However, you're not going to give this transistor a perfect control signal, and there are other factors that degrade this rating as well, so it's probably not a bad idea to calculate with a 20 to 30% derated value here. Multiply that by the current it will need to switch, squared, and you'll get the thermal power generated in the MOSFET in watts. So for a typical 12 volt heater cartridge with about 4 amps, that's roughly 0.4 watts that the IRLZ44N will turn into heat. For a 12 amp heater PCB, it comes up to 3.8 watts. Because the current is squared here, having 3 times the current actually makes for a factor of 9 when it comes to thermal losses. Now, these losses also need to escape the package somehow, and the datasheet also gives you a value for that, which is the thermal resistance. Junction to ambient if you're not using a heatsink. If you do have one screwed to the transistor, use its datasheet value for the thermal resistance instead. That value basically tells you how much the package will heat up for each watt of thermal losses. So in this case, without a heatsink, it's 62 degrees Celsius for each watt. So for the 0.4 watts with the heater cartridge, no heatsink and no airflow, it's going to heat roughly 25 degrees beyond ambient for a total of 45 to 50 degrees. With the load from a PCB heater bed, you'd end up with a rise of 236 degrees and a total of almost 250 degrees Celsius. Now, don't get me wrong when I say the MOSFET will probably keep working at those temperatures beyond its rated maximum of 175 degrees Celsius, but it's probably also going to desolder itself or light some stuff on fire. Not cool in quite a few different ways. So in this case, you're either going to need a heatsink or a better MOSFET with a lower DC resistance. Now, the other thing you'll need to look out for are the necessary drive levels for the MOSFET. The IRLZ44N is a logic level type, which means it should reach the specified on resistance at least when it's driven from a 5-volt source, so for example any of the common Arduino based boards. Other boards, like more modern ARM based ones like the Smoothie board or Replicate, are 3.3 volt systems and consequently also only provide roughly 3.3 amps for driving a MOSFET, so watch out for that. You can verify how well a MOSFET will do with a specific drive voltage, again in the datasheet, with the static drain source resistance at your specific drive voltage, so for example 5 volt or more realistically 4.5 volts here. You can see that with a 5 volt drive, the guaranteed on resistance already jumped to 25 milliohm compared to the front page rating of 22, which only applies if you use a full 10 volts to drive it, and if your drive voltage drops from the full 5 volts, the MOSFET's resistance will rise even further. By the way, this is the resistance value you should be using when calculating the losses inside the transistor, hence the 20 to 30% fudge factor. If you compare this to the much cheaper IRFC44N, which is not a logic level type, but still used incorrectly for that application way too often, we see that it doesn't even have a rating for a 5 volt drive. So this guy will waste a lot of power and get really hot if it needs to drive something like a heated bed with a 5 volt control signal. So that's how you can verify if a MOSFET is a good choice or not for a specific application. As a good basic choice, the IRLZ44N will work fine for any load in the same ballpark as a hot end. The only slightly more expensive IRF3708 will do a good job even for more demanding loads like a typical heated bed. Or if you need something a bit more hardcore, grab the IRLR8743, which gives you an even lower on resistance, but is not commonly available in the convenient through-hole packages like TO220, this one. So how do you wire it up? I mean, it only has 3 pins, there's not much that can go wrong. Typically, those 3 pins are gate, drain, and source in that order. Basically, gate is your control port, drain is where, figuratively, the current will drain into, and source is where it comes pouring out again. For the N-channel type MOSFETs we'll be using, when the MOSFET is turned off, it will block current from flowing from drain to source. When it's on, it will allow current to flow through. To turn it on, the gate needs to be at a significantly higher voltage than the drain, and to turn it off, at about the same or low voltage relative to the drain. The exact levels vary depending on which exact MOSFET you choose. So what we are going to, and actually pretty much all RepRap control boards are using, is called low side switching, where we'll disconnect our load from the ground line. So in the on state, of course, we'll have current flowing through this entire thing, but when we turn it off, because the current now can't flow through the MOSFET's drain will charge up through the load to the voltage level of the supply voltage. So that's how it should be wired up. Gate goes to your microcontroller's output pin. If you want it to be really perfect, you can add a 10 to 100 ohm resistor in series here. Then the drain goes to the negative terminal of your load, while the source goes directly to ground. Also, very important is a pull-down resistor on the gate, typically somewhere around 10K, so you can solder this one directly across the MOSFET's body, and it will protect it from going into an undefined state where the MOSFET will mostly work as a resistor and burn up. Lastly, the positive terminal of your load goes directly to the supply voltage. And that's really all there is to it. So again, there are only very few cases where we actually need a DC-DC solid state relay, and most of the time a MOSFET is the better and cheaper choice, as long as you pick a decent one. As always, thanks for watching, and I'll see you all in the next one.